Hey guys, today we're talking about constant rate of change and what it means to have a linear relationship. Okay, so if it's a straight line graph, then this is called a linear relationship. So if we look at this table, for example, notice that the number of songs increases by 2 and the minutes in time increase by 1. So what we're saying here is that the rate of change between 2 points is the same constant. So if I take 2 over 1, it's 2. Or 4 over 2, it's 2. Or 6 over 3, it's 2. Or 8 over 4, it's 2. We don't look at the point of origin, which is 0, 0, because if we look there, that's just talking about that it's going through the center point. And you can't really tell what's happening between from this point to this point. So the reason why we don't use that one is because we're looking at the change that's going on between 2 points, not necessarily the point itself. Okay, so the rate of change between any 2 points is a constant linear change. Okay, so what about this one? The balance in an account after several transactions is what we see here. So if we look at each one, is this transaction linear? So from 3 to 6, what's going on? We have an increase of 3. And over here, what do we have? A decrease of 30. So every 3 transactions is decreasing $30. So what that means is as the number of transactions increase by 3, the balance of the account decreases by 30. Okay, it's important that we understand what's happening in the table and that we're able to communicate it with our words. So, since the rate of change is a constant, there's a linear relationship. So if it's going up, increasing at a constant rate, and decreasing at a constant rate, it's a linear relationship. So the constant rate of change would be always your dV over your IV. You should remember that from science. Your dependent variable, I didn't mean to move that, over your independent variable. Let's move that back. Okay. So the reason why is because the independent variable supports or holds up the dependent variable. So we take our negative 30, that's our dependent variable, and it depends on the number of transactions, which goes in the bottom, the independent variable. So $10 per transaction, which means each transaction involves a $10 withdrawal. All right, so proportional linear relationships. In order for something to be a proportion, they have to have a constant ratio or a constant rate of change, okay? So, for example, B over A is constant, and the change in B over the change in A is constant. To determine if two quantities are proportional, we compare their ratios for several pairs of points to determine if there's a constant ratio. Okay, so the first thing that we need to look at is the change in the dVs. So it's an increase of 6 both times. So that is a constant. Over here, the chairs is an increase of 5. So that's a constant. So the change in our IV goes on the bottom and our dV goes on top. So 6/5. So that is our rate of change. Now we have to determine if the points are constant ratios. Basically, now this was our rate of change. So to determine if they're proportional, we have to see if each one of these is equivalent. So is 6/5 equivalent to 10/12, or not 10/12, I put that on the wrong way. Sorry, 12/10. There we go, Petruska. And if that is also equivalent to 18/15. Well, the way that we can do that is we can simplify these fractions. 12 and 10 share a 2 in common, so 6/5. 8 and 15 share a 3 in common, so 18 divided by 3 is 6, 15 divided by 3 is 5. Are all of these then equivalent ratios? The answer is yes, so this is a proportional relationship. Another thing that you can do and that you need to do is make sure that it passes through the point of origin. I added another loopy on there. Proportional relationship. I was doing proportional with relation. Okay, so what we need to do is we need to think, okay, if I went backwards, what would be the starting point? If I take 5 away, I'm back at 0, and if I take 6 away, I'm back at 0. So it also needs to pass through the point of origin. Okay, make sure that you have that down. It's got to pass through the point of origin, and all the ratios need to be equal. Let's look at this one, okay? Go ahead and try this one on your own. Use the table to determine if there's a proportional linear relationship between a temperature in degrees Fahrenheit and the temperature in degrees Celsius. So looking at this, what's the rate of change? Find that first, the constant rate of change, and then look at your dVs over your IVs, okay? And see what happens. All right, pause the video, go ahead and try it. I'm gonna go through it right now. So if we look at the dependent variable, okay, down here, everything is increasing by 9. If I look at the independent variable, everything is increasing, or excuse me, the dependent variable, everything's increasing. No, I was right. The independent variable is increasing by 5. So if I put my IV on the bottom and my dV on top, I'm finding the change in Fahrenheit, which this is always your Y, this is always your X, and which means this is always your dependent variable, and this one's always your independent variable. Whatever you input is your independent variable to get an output. Okay, so the change is going to be 9/5. So now what we need to do, we know that there's a linear relationship because it's constant. We need to figure out if there's going to be a proportional relationship. So the constant rate of change tells you it's a linear relationship. We need to know if it's now a proportional relationship. So we need to take each one of these different numbers and figure out what they would be if they were simplified. So 41/5 would be 8 2/10. 50 over 10 would be 5. 59 over 15 would be 3 9/10. So we know that these ratios are not the same, which means it's not a proportion. Okay, so we can even check our work by graphing. So if we graph this, we can see that it's a linear relationship, and all the points connect to form one. But notice that it doesn't pass through the origin. That means that it's not proportional. So like we talked about in the previous slide, if it doesn't pass through the origin, it's not a proportion. Okay, so what makes a graph linear and what does it look like? We kind of talked about those. Linear graphs have a constant rate of change and they form a straight line. So that's just a little bit to recap. So if we look at these, each one of these is a technically straight line. So we need to look at if they're increasing or decreasing or neither, because when we look at rate of change, sometimes it's positive, sometimes it's negative, sometimes it's increasing, sometimes it's decreasing, and we can find that from seeing if it's positive or negative. So if we look at this line, notice that if I look from the left to the right, it's increasing. This one is neutral from the left to the right, so it's neither. And this one, if I look from the left to the right, it's decreasing. This would be a negative rate of change. While this one would be a positive rate of change. Okay, so go ahead and see if you can count the rate of change for each line by figuring out what the rise over the run would be. So if we look at this, we're going to find the rise over the run, which is really the difference between our dependent variables and our independent variables. We can look and we're saying, okay, it's increasing by 2. And the x is increasing by 3, so they're both positive. So this would be a positive 2/3 as the rate of change, which is increasing because it's positive. If we look at this one, from this point to this point, I'm going down 1, 2, and I'm going over 1, 2, 3. So this one would be a negative 2/3 as my rate of change, which is decreasing. What if you looked at it from this point to this point? Okay, so yeah, it's going up to, let's do that in a different color so you can see it, up to, but it's going back 1, 2, 3. So it would still be a negative 2/3. It doesn't matter which point you start with. You have to look at, okay, from 4 to 1, that's going down. So it's a negative. Okay, let's look at these two. Go ahead and try this one on your own. Pause the video. I'm going to go through it. We're going to go up 1, 2, 3. And we're going over 1, 2, 3. So it's actually, if we simplify this, got a constant rate of change of 1. Here, I'm going up 1, 2, 3, 4, and I'm going back 1, 2. So this would have a rate of change of negative 2. If I looked at the other point, I'm going down 1, 2, 3, 4, and over 1, 2. So it's still a negative 2. Now, do you have to do both? No, you can just do one. Okay? But I'm showing you with both so that way you know. Okay, so let's look at these two. Count the rate of change for each one. Okay, it's going up. No. It's going down. No. Okay, so if I look at the rise over the run, it's not increasing or decreasing anything. So that's 0. But it is running 1, 2, 3, 4, 5. And if I have nothing and I divide it by 5 people, everybody gets nothing. So this rate of change is actually 0. If we look at this one, the rate of change, we rise 1, 2, 3, 4, 5, 6, 7. And we run 1, 2, 3. So 7 over 3. And we can leave it in this form. We can leave it improper. So this one, would that be increasing or decreasing? This one's an increasing. Let's go back. This one would be neither. Let's go back to our previous two slides. This one, since it's positive, it's increasing. And you can just tell by looking at it, right? And since this one is negative, it's decreasing. So that's one way that you can double check your work. If you see that a line is decreasing, then you know it's got to be a negative rate of change. If you see that a line is increasing, you know that it's a positive rate of change. All right, and that's all I have for you today. See you next time.